In this video, we want to transition a little bit to talking about subspaces or linear subspaces. And the other thing that we want to say in review is that we've been talking about these ideas of R2 space, which we know is the XY plane, two-dimensional space, and R3 space, which we know is three-dimensional space. It's the XYZ three-dimensional coordinate system. And the other way to think about these spaces is that R2 is really just made up of all two-dimensional vectors. In other words, every vector with two components. So every vector, we'll call them V, equals XY. And R3, three-dimensional space, is really just made up of all the three-dimensional vectors, or every vector you can imagine in the form XYZ with three components. In other words, if I take every three-dimensional vector I can come up with and put them all together, I'm going to have R3 coordinate space. If I take every possible two-dimensional vector and put them all together, I'm going to have two-dimensional space R2. And of course, I can keep this going all the way down through R4, R5, all the way down to Rn space, which is made up of all n-dimensional vectors, where my vectors are in the form V is equal to, and we could really think about this instead of using X, Y, Z, we'll use V sub 1, V sub 2, V sub 3, all the way to V sub n. It's going to have n components in the same way that we have three components here and two components here. Here we'll have n components. So we want to understand R2, R3, and Rn as spaces. They are spaces made up of all of the associated vectors. R2 is the space or subspace made up of all the two-dimensional vectors. But within these spaces, there are subspaces, and a subspace is defined in a particular way. So we want to talk about the three criteria, which is actually going to become two criteria, but the three criteria that define a subspace. So technically, a subspace has to meet three conditions. The first is that it must always include the zero vector. That's one requirement. The second is that it's closed under scalar multiplication. And the third is that it's closed under addition. So let's go over each one of these conditions briefly so that we know in general what they mean, and then we'll go through an example so we can actually apply this so that you can see how to determine whether or not a vector set represents a subspace. So in order to be able to call a set of vectors a subspace, in order to define it, technically speaking, as a subspace, that vector set has to include the zero vector. That one's fairly straightforward. The zero vector has to be part of the set. It's the other two that are trickier. So to be closed under scalar multiplication means that I have to be able to take any vector in the set, multiply it by a scalar, and still get another vector that's already included in the set. So for instance, if I have the vector set V, and in the vector set, I have a bunch of vectors, V1, V2, V3, V4, and so on. So I have a bunch of vectors in my vector set V. I need to be able to take any vector in the set. Let's say I choose V3. So I need to be able to take V3 and multiply it by a scalar, which we'll call C. C times V3 must still be in my vector set somewhere in order for the set V to be closed under scalar multiplication. If I can multiply V3 by any scalar, C, and get a vector that isn't already included as part of the set V, then V is not closed under multiplication. And I have to be able to do that with every single vector in the set. So I need to be able to multiply V1 by any scalar that I want to. I need to be able to multiply V2 by any scalar that I want to, multiply V3 by any scalar that I want to. And every single time, I have to end up with a vector that was already part of V originally. If I do, then V is closed under scalar multiplication. If I don't, then it's not closed under scalar multiplication. Being closed under addition is a similar thing. So again, I have this same vector set V with all these vectors included, V1, V2, V3, V4, etc. I need to be able to take any two vectors. Let's say I want to take V2 and V4, and I need to be able to add them together. So V2 and V4. Their sum, of course, will also be a vector. Whatever that vector is, that vector, that sum, also has to have been part of the original vector set V. If it is, then V is closed under addition. If it's not, then V is not closed under addition. And just like with the scalar multiplication, I have to be able to choose any vectors that I want to. So I have to be able to add V1 and V4, or V3 and V1, or V2 and V1. I can pick any vectors that I want to, add them together, and I must get another vector that was already in the set V originally. And again, in order for V to be a subspace, I must meet all three of these conditions. Otherwise, if I fail to meet one or multiple of these conditions, then V is not a subspace. It cannot be called a subspace. Now, one thing we want to say is that we can actually simplify this definition because we're saying that the subspace must include the zero vector, and we're also saying that the subspace must be closed under scalar multiplication. But when we talked about scalar multiplication, we said that we could choose any scalar, c, to multiply by a vector. Well, that includes the zero scalar. I can choose c equals 0. So if I choose c equals 0, then I'm obviously going to get the zero vector, because when I multiply 0 by any other vector, I'm going to get the zero vector. So if the space is closed under scalar multiplication, then that automatically implies that the subspace includes the zero vector. You sort of get this one thrown in for free. So actually, when we're looking at the definition of a subspace, we really only have to check these two things. We have to check to see that it's closed under scalar multiplication, and we have to check to see that it's closed under addition. And if it meets those two conditions, then it's a subspace. So let's look at an example so that we can actually get a better understanding of what we're talking about. So let's say that we have a vector set V, and this vector set is going to be all the vectors, we'll call them generically just xy. So it's going to be any vector xy that is in R2, this symbol here means in, so in R2, such that x plus y is equal to 0. And so we can imagine some of the vectors that would be included in this set. We have to meet this condition here that x plus y is going to equal 0. So we could, for instance, have the vector -1, 1. We could have the vector, let's say, 3, -3. We could have the vector 0, 0. And we could think of course, a ton more. But as long as when we sum these two components, they equal 0, that vector is going to be included in the set. So let's think about this here. Let's look at each of our conditions. Let's first talk about scalar multiplication being closed under scalar multiplication. If I take any vector in the set, and actually let's start with the generic vector xy, if this condition is true here, I could actually subtract y from both sides of this, and I can see that I get x is equal to -y. Of course, it would also be true here that if I multiplied both sides by -1, y is equal to -x. So both of these are natural outcomes from this x plus y equals 0, which means that I could rewrite this generic vector here. I could say that all of the vectors that are in the vector set V, instead of y, I could use this substitution here. I said y is equal to -x, so I know my vector set V is going to include all vectors in the form x, -x, or alternatively, -y, y. Now those are generic vectors that would be included in the set. If I multiply this by a scalar, so let's say I multiply this vector x, -x by a scalar c, so I'm going to have c times x, -x, the vector I'm going to get here is cx -cx. Well, remember that my condition here, x plus y equals 0, is telling me that if I add these two together, I have to get 0. So I have to be able to say cx plus negative cx equals 0. I get cx minus cx equals 0, or 0 equals 0. This checks out, which means the vector cx, negative cx, is in the vector set V. So I took a generic vector in the set V, I multiplied it by a scalar, and I got a vector that was still in the set V. And this is really the same thing, but even if we took this generic version, negative y, y, if we multiplied that by a scalar, so c times negative y, y, we're going to get negative cy and then cy. And of course, if we add those together, negative cy plus cy equals 0, we're going to get 0 equals 0, and that checks out as well. So no matter which vector I start with in V, a vector that's already in the set V, if I multiply it by a scalar, I'm still going to get back to another vector that is included in the original set V. So the vector set V is closed under scalar multiplication. And as you can see, that of course means that it includes the 0 vector, because if I take the vector 0, 0 in the set V, that means that x plus y equals 0, 0 plus 0 equals 0, or 0 equals 0. That's true. So the 0 vector meets this condition. It's also included in the set. Now to check to see whether the set is closed under addition, I again just need to take a generic vector that's part of the set. We'll take this x, negative x. And if I add it to another generic vector in the set, we'll say we'll add it to this negative y, y, I'll get this vector addition problem. So I'll get x, negative x, plus, and then here, negative y, y. And the sum here is going to be x minus y and negative x plus y. Or I could rewrite that as x minus y and y minus x. And so now what I'm interested in is whether or not this vector is included in the original set V. Well, as long as it meets this condition, x plus y equals 0, then I know that this is also included in the original vector set V, and therefore the set would be closed under addition. So I just need to plug these in for x and y. So instead of x plus y equals 0, I'll take my x component, x minus y, and then add that to the y component, y minus x, and I should get 0. And in fact, I do. I can see my negative y and y cancel out and become 0. My x minus x gives me 0, so I'm left with 0 equals 0. That checks out, and I can see that the set is also closed under addition. So because the vector set V is closed under scalar multiplication and closed under addition, it meets all three conditions for being a subspace, and I can say that V technically is a subspace. And furthermore, because V is defined in terms of two-dimensional vectors, I can say that this is a subspace of two-dimensional space R2. If I had done this whole thing in three-dimensional vectors, if V was a set of three-dimensional vectors, then V would have been a subspace of R3. But because we're in two-dimensional vectors, this is a subspace of R2.